Yes. Is that what you were going to ask? 24. Okay. Oh, oh yeah. 24. This is foreshadowing. This is rigid body kinematics. No, just particle kinematics. In a non-rotating coordinate system, number 24. Anybody have any theories about this? So the idea is like we can do kinematics of a linkage like this. We can't do kinematics of a linkage like this. All right, well, the difference between these two is that everything here is moving in the plane, right? And here, this thing is moving in the plane, but this thing's swinging out and around. Mathematically, the reason that we can do this and not that one is that the axis of rotation of this second piece isn't affected by the motion of the first piece. So you always have one thing riding the other one, right? But the sort of the thing that this one is riding doesn't change the axis of rotation. This one, though, as this one rotates, the axis that this one rotates around is changing in time, okay? And so what is the, what's the omega vector and what's the angular acceleration vector of this thing if the axis is moving in time? There's really no way to just think through it on your own. So this one, the axis of rotation, let me call this body 1 and this body 2. This is body 1 and this is body 2. So in the one on the left, the axis of rotation of 2 is constant. In the one on the right, the axis of rotation of 2 depends on the motion of 1. When we do problems like the one on the right later in this class, we're going to do it by fixing a coordinate system to body 1. Okay, if you do that, if you say like the x-axis is parallel to long axis of 1, then it's easy to calculate in that coordinate system. It's easy to calculate the motion of 2, right? And in that coordinate system, the axis of rotation is constant. But it creates a new problem. Now, as member 1 is moving, your coordinate system is rotating. Okay. So this is the main type of problem that we're going to do with a rotating coordinate system. Okay. This one, we don't need to do that. We can fix our coordinate system like here, like this, and then the axes of rotation are just in the z direction no matter what. Any other questions about that one? Any other homework questions? Okay. That was just because my computer shocked me and it like disrupted the. All right, so now we're going on to particle kinetics. So let's just get the terminology straight. Kinematics is the it's just about describing the motion of objects. Without considering the causes. So we don't use mass, force, energy, charge. We're not going to talk about charge in this class. I suppose we could. Basically, kinematics is just all the stuff that you could measure from a video of something. Like if there's any way you could set up a video camera to measure something's motion, then that's kinematics. Kinetics is just combining kinematics. So it includes kinematics. And then we include the causes. So for us, this is where Newton's laws are going to come into it, because now we're going to deal with mass and force. Since we're only dealing with particles, we're not considering length dimensions of any objects. And if there's no length dimensions, there's no difference between the left side and right side and top and bottom. And so we also can't consider orientations. And so we're not going to consider moments of inertia, any of that stuff. The only equation of motion that's an equation that relates the causes to the kinematics for particles is Newton's second law. I'm going to always abbreviate that N2L. And that says that if you add up all the forces to make F net, all the forces on a chosen object, that's equal to the mass of the chosen object times the acceleration of the object's center of mass. So F net is sum of the forces on the chosen object M is the mass of the chosen object. And ACOM is the acceleration of the chosen object's center of mass. So this idea of what your chosen object is going to be crucial to all of this. And that's where free body diagrams come in. And anytime you use Newton's second law, um, so to be clear about what is your chosen object, you must draw a free body diagram and I love abbreviations, so I'm going to call that FPD. For every application of Newton's second law, and this is particles, so we're not going to have the moment equation yet, but this is also going to be true of the moment equation. Okay. Well, there's one time. Well, unless you just want to calculate the net force. If you don't care about any of the individual forces, then there's not really any benefit in drawing a free body diagram. You can, but it's going to always look the same. It's going to be a blob in the shape of your thing with a net force drawn on it, you know, if you're not separating it up into individual things. But okay, so let's talk about what I want to see on free body diagrams. So first, draw a closed outline of the body that you've chosen. Closed outline of the chosen body. So if body you're isolating is this person, gingerbread man. Okay, that's a closed outline. The outline goes all the way around and connects at one end. And it's totally unambiguous what's on the inside and what's on the outside. That's what this is all about. So this is not. That doesn't have an inside and an outside, so don't do that. And there should be no internal details or external objects. So, ooh, this car looks fast. Oh, no, not so much anymore. Oh, that's a closed outline of a car. But if you're isolating the car, this is a better picture of a car, arguably. But that's a worse free body diagram because all you're trying to do in the free body diagram is communicate the boundary between the stuff that's in and the stuff that's out. Okay, and all those lines are just confusing. And then the external details, the ground there, Now, like, what's that? Like, are we including part of the ground in our chosen body? Do we have to consider forces that some of the ground applies to other parts of the ground? So the line that you want just defines the distinction between what you're choosing and everything else. Okay. Um, Now include all external loads. And when I say loads, I'm talking about mostly forces, but anytime you have couples, uh, most of you have taken statics, and a couple is made up of two equal and opposite forces, and we just think of those as like a pure moment. So forces and couples are both types of loads. Um, so break this up into two types. If the force direction is known, draw an arrow in that direction. And label it with a scalar. Okay, so forces are always vectors. Forces always have both a magnitude and a direction. But if you know the direction of a force, you draw an arrow in the direction that you know that force applies. And now you don't need to specify it with a vector variable anymore. Now all you need, since you already know that direction, all you need to fully specify that vector is a magnitude. Okay, and so in this case, so if you're isolating this car, and it's pulling on this car with a cable, you know the direction of that force is to the right, and so the variable you need to associate it with is just the magnitude. It's a scalar. Okay. On the other hand, if the force direction is unknown, then draw components in the direction of the coordinate axes of the coordinate system axes and label with a vector. Okay, so if this car is like stuck in the mud, you don't know the direction of the force the mud's applying to the wheels, and so you just draw it like this, components in both of the two directions if you're doing a problem in the plane, and label it with. And a lot of people do it like this too. Maybe more people do it like this. I'm just not in the habit of doing it, but that's fine too. You can do it like that and call it fx and fy. That's no different. If you just want to show me that you're your own person and you don't have to do exactly what I tell you to do, you can do that too. Okay. I always get like people come to me in physics 1 and like statics and stuff, and they're like, you know, you said to do it like this, but I do it like this. Is that all right? I'm like, you don't do anything. You've been doing this for like 2 minutes. I'm telling you how to start doing things. You do what I say. I'm not talking about you guys though. Okay, so the free body diagram, that's the end of it. That's all. Uh, the free body diagram must account for every load that's applied to an object. Applied to the object by the surroundings. Like for example, some examples of forces that are acting on this car are the force, the piston, one of the pistons applies to the cylinder, right? Because the cylinder is part of the car. The piston is too, but I mean, that's a force being applied to the car. We don't have to account for those though. Those are happening inside the boundary. Okay, so the only things we have to account for are external forces. And that's good because I mean, imagine if we were trying to deal with all, like, it simplifies things a lot. We don't want to have to deal with all the molecular forces and whatever going on. Um, so how do you know when you've got them all? Bless you. Um, when you've got them all. So sometimes you look at a problem and it just looks so complicated and your brain just sort of short circuits, you know. But this is sort of a systematic way to just remind yourself, like, okay, just do this and do this and do this, and then you know you have them. Um, there are only two types of forces. Um, the first one is field forces, force fields. Um, for us, that's mainly gravity. Gravity is by far the one we're going to use the most. But it also includes electric fields if you have charged particles. Um, magnetic fields, and there are probably other types, but that's all that occurs to me right now. And so mainly, the first thing you have to account for is gravity. So you isolate your object, you account for gravity. There's a downward force of gravity. That's easy to do. And then besides that, the only other force that you have to deal with are contact forces applied to the chosen object by the surroundings at the boundary. Okay, so that idea of drawing a closed outline of the object that you're isolating, what you've drawn is the boundary between what's in and what's out. And once you've drawn the weight force, all that there is left to do is go around the boundary of the object and choose the places where the surroundings make contact with it. If there's no contact between the surroundings and the boundary, then there's nothing. Well, you know, air, in some cases, air resistance could be a contact. So that, but all you're doing is going around the boundary and saying, here's one, here's one, here's one. Once you've gone all the way around the boundary, you're done. You know you've accounted for everything. In 3D, you have to go around that whole surface area, you know. So it's not just following the line around. You have to imagine going around the whole thing, but it's still the same idea. Okay, so let me show an example of this. Okay, so let's say here's the ocean, and here's like this pickup truck is sort of sinking. And there's a pig in the back of the pickup truck. Sort of looks like a cow, but it's a pig. And there's some kind of giant seabird standing on the pig. That's, well, we're not isolating the bottom of the sea, so we don't care. And then the Coast Guard is working without pay because of the government shutdown, but they're still trying to get this truck out of there. Okay, so draw a free body diagram of what do we want to isolate? Well, let's first do the truck. It's not a very good truck, but closed outline of the truck. Okay. And now we apply the weight force. Whether something's in water or not, gravity treats it the same. So we have mg down, I guess mtg for the mass of the truck. And then we have a force vector applied by the water. And then we have a pulling force from the cable. And then we have a downward force applied by the pig. And there's nothing else in here. So there's the weight force. Then we went around the boundary and found the 3 places where the surroundings are touching the boundary. There's no force from the helicopter because the helicopter isn't touching the truck. There's no force from the bird because the bird isn't touching the truck. Okay, so now we know we're done. And a free body diagram of the pig. Okay, that's a closed outline of the pig. So what forces are acting on the pig? There's the weight force. That's the mass of the pig times gravity. There's a force pushing up from the truck. There's a force pushing down from the bird. The cable, the helicopter, the water, none of that stuff is touching the boundary of the pig, so that doesn't appear in the free body diagram. Okay, that stuff only communicates directly through those contact forces. Anybody have any questions? Well, we'll get to that a little more. in this case, I sort of made some assumptions about what kind of force the pig is applying to the truck, and I didn't make any assumptions about the force the water is applying to the truck. But we'll talk about that in like case by case. Yes. Thank you. This is a vector, and this is a vector. And those, no, this one is not. So okay, no, let me think about this again. I was sloppy there. The force on the truck from the water is a vector. I assumed we didn't know anything about that direction, and so I drew two different components of force. And so, yeah, that variable should have a vector symbol over it. All of the other ones are just given as arrows, and so we're assuming we know the directions of those forces, and so those should be associated with scalars. Okay, so now it's right. Scalar, 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 and this one's a vector. And on the pig, everything's a scalar because I was assuming we know the directions of all those forces. I'm glad you asked that because that was sloppy. But yeah, when you have a vector variable, you should always put a vector symbol over it. I mean, I can't imagine I would ever take points off, but you know, largely what you're trying to do here is communicate to other people with your free body diagrams and stuff. Later on, especially like when you're working, this is a way you're going to communicate, and that vector symbol helps communicate what you're talking about a lot. Any other questions? So now the double subscript notation for force. Okay, so we're not going to use this for scalars. We are also going to use it for couples. Not yet, because these are particles. So before I do this, notice you don't want to use this for scalars. You don't want to use this for scalar forces associated with known directions. If you do, it's really easy to get directions backwards when you use Newton's third law. So that's why we're not going to do it. But the double subscript notation says that the force sub AB is the force vector on body A applied by body B. Okay, so if you use that double subscript notation and in your head you're thinking the force A applies to B, then you're getting that backwards. If you want to be really clear about it, you could, it just takes more time, but you could write F on A by B, or if you're going to be that clear about it anyways, you could, if you want, write it the force IB on A. That's, but if you write it just with that double subscript notation, I'm going to interpret that as the force on body A by body B. And people use this notation because it's quicker. The thing that's a nuisance about it is, for the most part, engineers use this to mean the force on A by B, like I'm using it. And physics people tend to use that to mean the force A applies to B, the exact opposite meaning. So that's a pain, and I don't have a solution for that. But and so to really be clear about communicating what you're talking about to anybody, you'd have to write it like this, you know, force on A by B, or sometimes people write it force B on A. And I know, like in Tony Weinbeck's calc-based physics class, when he uses this double subscript notation, he means the exact opposite of what I do, and that's a bummer, but that's how it is. Anybody have any questions about that? All right. Well, the benefit of this double subscript notation comes up in Newton's third law. And because of my love for abbreviations, I'm going to call this NPL. That's the one that says for every action, there's a equal and opposite reaction. Making sense out of that is sort of confusing. But mathematically, the way we're going to do it is really easy to interpret. The way we are going to interpret this is just the force on A by B is equal to negative force on B by A. So if you switch the subscripts, you flip the sign. And that means flipping the sign of both of the components or all the components. For forces with known directions, I'll be using that double subscript notation because the variables you're talking about are scalars. So Newton's third law with forces with known directions work like this. If you have two objects that are in contact, so let's say this is body A and this is body B. Then the free body diagram of A looks like this. And you can label that with whatever scalar variable you want. And then the free body diagram of the other body that's in contact with the first one has the arrow in the exact opposite direction with the same variable representing it. Notice, by the way, that this whole thing together the direction combined with that magnitude R, that is the force on A by B. And this whole thing here is the force on B by A. And you can see that the way we've done it, that's equal to negative force on A by B. So it's still doing the same thing. It's just you won't have written out that double subscript notation if your variable is a scalar. Okay, so one more thing, one more question. Why do we only care about, so in Newton's second law, do we only care about loads that are applied to the chosen body by the surroundings? The answer is that the internal loads, which are also loads applied to the chosen body, and you might think at first that you have to add those in, always occur in equal and opposite pairs at the same location because of Newton's third law. So Newton's third law says that internal loads in equal and opposite pairs at the same location, and so they cancel out. So if you're isolating a truck that's running, the engine, parts of the engine, like say the piston is applying a big force to the cylinder, right? But at the same location, and that the cylinder is part of the truck, so that's a force on the truck. But at the same location, the cylinder is applying an equal and opposite force to the piston, and that piston is also part of the truck. So those two forces cancel out. And that happens with every internal force. When you get to the boundary, though, the surroundings, like the pig, is applying a force to the truck. The truck's applying an equal and opposite force to the pig, but the pig is not part of the truck. So you only get half of that pair in your body. And that's why the only stuff that we care about is the stuff happening at the boundary and gravity. Yep. Mm-hmm. Yeah, well, those are called internal forces, but remember, those were not internal to our chosen object. The way we found those is we made a cut, and then our chosen object was only part of that beam, So we were still just calculating the external forces on a part of the beam. Then we called it internal because we sort of have this intuitive idea in our head that a beam is a thing, But physics-wise, your chosen object is whatever you choose it to be. It could be a tiny part of something or 100 things combined together, or, So we decide what's internal and what's external. Any other questions? Okay. Have a good weekend. See you on Wednesday. No, it's President's Day on Monday. No school on Monday. Also, Wednesday is my birthday. I turned 46. So I'll see you on my birthday. Probably not. But if I have any, I'll give it to you. I'll give you some.